My name is Yuki Naito. I belong to University of Tokyo. My research topic is the study of heave and roll and pitch motion in flow of lightweight floating offshore wind turbine. My research analyzes the effect of vortex on the pontoon of semi-subtype floating offshore wind turbine. Wind power generation is currently attracting attention around the world. In particular, floating offshore wind turbines are under development. One new form of floating offshore wind turbine is OptiFlow. OptiFlow has several features. One of the first, lightweighting with guy wire. Second, it is a semi-subtype floating structure. OptiFlow has longer and thicker pontoon than normal semi-subtype. In this study, I defined the horizon part of floating as a pontoon, and the vertical column as a column. Third, it is a single point mooring. With a single point mooring, floating body perceptibly follows wind direction. When the follow and window direction are different, the turning motion may result in a relative increase in follow velocity. Next, I will discuss vortex-induced motion. Structure in a flow has vortexes behind the object due to detachment of boundary layer. This vortex affects the object and causes vibration. The amplitude of this vibration is determined by the reduced velocity VR. Reduced velocity VR is expressed by this equation. Vertical vibration of the flow includes with VR around the 5 to 8. In a lightweight semi-subtype floating structure such as OptiFlow, the motion caused by this vortex may not be ignored. Since floating offshore wind turbines are expected to be lighter in the future, such as the OptiFlow, it is necessary to analyze the effect of vortex-induced motion on the light floating structure. There have been several previous studies, but there are no papers on lightweight floats, nor on vortex-induced motion for pontoons. Vortex-induced motion to pontoons cause vertical vibration, heave, roll, and pitch. It needs attention. My research purpose is the heave, roll, and pitch of the lightweight floating wind turbine due to vortex-induced motion analyzed. In this study, we will analyze the vibration caused by vortex-induced motion through experiment. First, design of experimental model. Next, planning of experimental condition. Experiment, analysis of experiment. This is design of experimental model. The model is in 1/60 scale. The weight is about as light as an OptiFlow. The form is similar to standard semi-subtype floating offshore wind turbine. To make it easy to generate vortexes, the pontoons are cylinder. Dimensions are shown in the table on the right. Next, I will discuss the experimental condition. The experiment was conducted by the Hongo campus of the University of Tokyo. The experiment conducted by changed two conditions, angle and velocity. In the angle condition, in order to analyze the turning test, it is necessary to analyze many angle conditions. So, 5 angle conditions are used: 0 degree, 15 degree, 30 degree, 45 degree, 60. In the velocity condition, when reduced velocity VR is from 5 to 8, the vibration becomes larger. So reduced velocity should be measured from the smallest condition to the condition of over 8. The follow velocity condition is from 0.05 meter per sec to 0.5 meter per sec, in increment of 0.01 meter per sec. I will discuss result of the experiment. The plan was to conduct the test in the range of 0.05 meter per sec to 0.5 meter per sec. But the test cancelled halfway, because floating structure would tip at the higher velocities, and the upper deck would be covered with water like this picture. Measurements were taken up to around 0.33 meter per sec in each condition. As shown in the lower right figure, the result of experiments shows that the vibrations were larger or smaller depending on time. The vertical axis is the z-directional displacement divided by the pontoon diameter. From the result, frequency, maximum amplitude, standard deviation, I used the evaluation standard in the analysis of the experiment. This is Heave result of experiment. Figure on left is relationship between standard deviation and reduced velocity on Heave. The vertical axis is the z-directional standard deviation divided by the pontoon diameter. Horizontal axis is reduced velocity. Figure on right is relationship between frequency and reduced velocity. The vertical axis is the frequency with largest spectra when FFT is performed, divided by the natural frequency. Horizontal axis is reduced velocity. In the reduced velocity, U use turning speed. Fc use natural frequency. D is diameter of pontoon. The maximum amplitude shows a similar trend to the standard deviation result. In frequency, more reduced velocity includes, the more frequency tend to increase. When reduced velocity around the 5 to 8, the frequency divided by natural frequency around 1. It is locking. The result suggested that vortex-induced motion is occurring. Next, this is pitch result of experiment. Figure on left is the relationship between standard deviation and reduced velocity on pitch. The vertical axis is the standard deviation in pitch multiplied by root 2. Horizontal axis is reduced velocity. Figure on right is the relationship between frequency and reduced velocity. The difference in vibration can be seen depending on the angle. In the 0 degree and 60 degree angle condition, there is a clear difference in the vibration between large and small. The amplitude is large at 0 degree and small at 60 degree. On 45 degree and 60 degree, frequency divided by natural frequency is close to 1, independent of the reduced velocity. This is the result of my research. That's all. Thank you for listening.